Okay, let's get started. Right, so this is our second lecture. We're going to talk about Boolean Algebra. So I want to first make a couple announcement. First is this first lab. We'll most likely release it tonight. We are cleaning up that handout. We will release it tomorrow morning at the latest. Right? Once we release it, we're going to release it on CMS. Okay. Once we release it, we also make an announcement on Piazza. Just want to make note that if you look at this lab, once you get the lab, it's mostly about Boolean function simplification. So which is something that we'll cover in the next lecture. Okay. So don't worry about that too much. So focus on the tutorial tool first. So there will be a tutorial on a CAD tool called Cordus. Okay. So this is something that you guys have to use from lab 2. In the past, actually some students have experienced some trouble installing the tool because depending on whether you are using a Mac or Windows machine or Linux, right, different students may have different issues. That's why we ask you guys to really start installing this tool as early as possible. We'll even have a pre-lab assignment for you guys to actually demonstrate that you have indeed successfully installed the tool, okay, on your computer. All right. And also, like I mentioned last time, we'll start the office hours from next week. In case you haven't noticed, there's actually a weekly calendar on the course website. There's where you can find all the TA office hours, and also my instructor office hour. Okay, so there's one PDF. And I also posted the lecture slides, actually the slide deck for today's lecture on the course website as well. Okay, that might be useful, right, in case you want to go back a few slides to check out what's going on. And also there'll be a quiz today. Right? You can also look at the lecture slides when you're doing a quiz. I'll try to post the slides at least 1 hour before the lecture. Okay, so that's something that I'll try to do. All right. Okay, so let's briefly review what we talked about last time. Right? Last time, we introduced this important concept called the digital abstraction. Right? One of the simplest kind of a digital system is this binary system, right? Just 0, 1. Right? You can. Last time we already did some exercise, right? We did a live challenge. Many different kind of things can be encoded using this binary system. You can encode high-low, right, true, false, on-off, right? Many different things. We'll actually see more in the few lecture. And in our system, right, so since this is an electronic system, we use voltage to indicate the logic level, right? So we usually use high voltage to indicate the high logic level, which is 1, and the low voltage for 0. So the nice thing about this binary system is that we can actually tolerate some noise, right? So that 0 cannot be easily confused with 1. So that's the key idea. I also just want to briefly remind everyone again, right? So digital system is really about having a finite set of values, right? So that's the key idea. Quick question. So, we talk about what is a digital system, but we haven't really talked much about what is not a digital system, right? So how about this one? How about 1/3? Is this something that we can represent digitally? If not, why not, right? Feel free to just turn on your mic, right, and chime in.
No, because it's a partial value.
Because it's a partial as a fractional, right? So what is 1/3? Right? So mathematically, right? So if you just calculate this, right, if you actually expand it out, this is going to be 0.333, right? A lot of 3s, right? Infinite number of 3s, right? So this is the precise value of 1/3, right? But this is kind of surprising, right? Because we talk about digital system, right? It's so powerful, right? We cannot even represent 1/3. What's going on, right? 1/3 is actually there's a fractional value, right? This is if we actually have to precisely store it in our memory or in our digital system, we actually need infinite number of bits. I think some of you are already mentioning this, right? So in the chat window. Okay. right? Of course, we can store this symbolically, right? So that's one way. And also one thing I want to make sure that you guys understand is, so actually some of you in the chat window already mentioned this keyword called quantization and quantize, right? So in many cases, we have to lose precision. We don't want to store this many digits, okay? So in realistic applications, right, in many cases, right, storing just a few digits, right, or maybe 10 digits, right, after the decimal points, or maybe a bit more, right, that's usually good enough, right? And in some other courses later on, you may also learn something called floating point value, which will allow you to have a much larger dynamic range, okay? All right, so hopefully this makes sense, right? This is not something that, we cannot represent, but, we have to sacrifice the precision. But in most cases, actually in most cases, this sacrifice, this compromise is not a big deal, right? Okay, so last time I also talked about this logic gates, right? This is another important concept, right? So this is basically where we can process the, this binary information, right? We introduce a NOT gate, AND gate, right? OR gate. So these are the symbols that we will use, right? So in the rest of the course, so these are the symbols. Okay, we use a lot. Okay, we use A prime usually, right, to indicate a NOT gate or inverter, and we use this product sign, right? Usually, in many cases, I'll just say A times B, when I actually mean A and B. Okay, so just want to be clear, right? And in many cases, instead of saying A or B, right, just for the sake of simplicity, I'll just say A plus B, right? So I'm still staying in the same binary system, although in some cases I'll just say plus and multiply or times. Okay, and also we want to be able to precisely define this, right? So the way to do this is to use this so-called truth table, right? Right, the truth table. Okay, so this is where we have the input columns and output columns, right? And also we enumerate all the possible input combinations. For 2 input functions, right, we have 4 rows, right? For 3 input functions, we have 8 rows. Okay, so just want to make sure that you guys are comfortable with the definition of this gates and also truth table. Let's look at another function, right? So this is another function which does not really have, right? Of course, we can come up with a closed form equation, but let me just define it this way. This is a 3 input function. Okay. Output is F, right? So I have A, B, C, right, being 3 inputs. Okay. So F is 1, right? F evaluates to 1 if A and B, right? A times B is not the same with B or C naught. Okay. Also, in many cases, I will either say C prime or C naught, okay, to indicate the inverter. All right, otherwise it's 0. Is it clear? So the reason I'm using this exercise is to make sure that you guys understand that it's not like we can only use truth table to represent the simple gates, right? NOT gate, OR gate, right? AND gate. We can actually use it to indicate, represent, express any arbitrary function. Right? Of course, if you have many inputs, right, many outputs, this table is going to be very complex. But we can use it to indicate and represent any arbitrary function. Okay. All right. Okay, so good question, right? There's the question, Moon is asking, why are there gaps, right? Right, very good. So these the empty, right, these ones. So these are the ones that I want you guys to fill out. Okay, let's just do this exercise. For the blue ones, those are the things that I already pre-calculated, right? If you trust me, of course you can verify, right? But let's just focus on the ones that are empty. Okay, let's look at this row. Okay, so what is A and B for this row? 0, 0, 1. 0, right? Okay, so B plus C naught, what is this? Again, 0, 0, 1. Is it 0 or 1? So B is 0, right? C is 1. C naught is 0. So 0 plus 0, we get a 0, right? Okay, so these two are the same, right? So that's why we have what? Over here, we have a 0. Does it make sense? Okay. All right, so then just tell me, right? So 1, 0, 0, okay. A times B again, so this is 0, right? For AND gate, you know, the moment you have a 0, if one of the input is 0, regardless of the other input, right? The output is going to be 0, right? We're going to learn this. There's something called NAR element. And B plus C naught, what is this? Okay, C naught is going to be 1, right? So for OR gate, if there's a 1, you don't care about the other input, right? The output is going to be 1, right? And they are not the same, right? So we have 1. Make sense? Okay. All right, last one, 1, 1, 0. Okay, just tell me. So I'll not compute A and B plus C naught. Just tell me, is it 0? So this one. They are the same, right? Convince yourself. Right? They are the same. Any questions? Most of you are getting this right? Very good. Okay, we'll see this same truth table again, okay, later on. Again, the point here is that, you know, we have a 3 input, right? Boolean function. So that's why we have 8 rows, right? And then we have a single output, right? Alma is asking, why is 1, 0, 1 a 1? Where's 1, 0, 1? Okay, I might be wrong, right? So let's just look at, so this one, right? Okay, you know, I might be making a mistake. Let's just, okay. 1, 0, 1, A and B is what? 0, right? Okay, B plus C naught, what is this? It's also 0, right? Okay, so they are not the same, is that right? So looks like I made a mistake. Yes or no? Okay. All right, so maybe this should be a 0, right? Okay, all right, very good. Very great catch. Okay, very good catch, Emma. All right, so, you know, this is actually the, hopefully now you guys are more or less comfortable, right? With the 0 and 1s, right? In the AND gate, OR gate, right? And this is actually gonna be the word, right? That we'll be living in this course, right? Everything is 0, 1. Okay, and some of you may still not be comfortable with this, right? You know, we do count in 10, right? I just want to briefly bring up, you know, this is a very fun fact, right? Actually, many of you might have heard of this Maya civilization, right? So they actually, this is Asian civilization, but they have actually developed something pretty advanced, right? They have their own mathematical system, right? They have their own architecture, right? They have their own, you know, there are actually many amazing things they have developed. But for some reason, the Maya people, the Mayans, actually count in 20, not 10, right? So we look at these ones, so these are their symbols, right? That's how they count from 0 to 20. Okay, so why is that? The answer is actually in the picture. Okay. Anyone can spot the reason? Why do they count in 20? And feel free to directly chime in. 20 fingers. Very good. Some of you already got it, right? Pietro is saying fingers plus toes, right? Just look at this, right? You know, that was in the detail, right? Okay, no shoes. Right? They don't wear shoes, right? So that's why they are counting in 20. And hopefully this will help you overcome a bit, right? So your discomfort with 0, 1s, you know, 10 is actually not a special number, at least mathematically, right? It just happened that we have 10 fingers, right? It's just a natural point to stop, right? and then 1 to the next level, right? So that's why we count in 10, right? Okay, cool. Okay, so today we're going to talk about Boolean algebra, right? So these are basically the rules, right? And some of the things that we have to pay attention to, the key rules when we live in this 0-1 world. And this is actually a mathematical foundation for analyzing and optimizing the circuits, the digital circuits that we're going to be using a lot. If you have already read the book, so Boolean algebra is invented, right? It's really proposed, introduced by George Boole, right? About 150 years ago. Okay, George Boole is a British mathematician. Okay, so in his book, he actually introduced this notion of the true false, right? This propositional sort of logic, and also there's a two-value system. He also introduced NOT gate and AND gate and OR gate. Okay, and actually George Boole is actually directly related to this technique that I mentioned, technology, deep learning, right? I mentioned deep learning in my first lecture, right? Now, of course, right, these days the deep learning, these AI systems are running on the digital computers, right? But actually one of the pioneers of deep learning is a Canadian researcher, Canadian professor, Geoff Hinton. Geoff Hinton actually won the Turing Prize 3 years ago in 2018 for his contributions to deep learning. Actually, Hinton is the great-great-grandson of George Boole. Okay, so they are actually related that way. And the other name I want to mention, so this is a really important name. Okay, in case you guys have not heard about this guy, right? Please try to remember this name as well. Right? Claude Shannon. Shannon is the one who invented sort of digital, in the sense that he invented digital circuits. He's the one who applied Boolean algebra to the optimization of this switching circuit. Okay, so that's why in many cases we are using Boolean algebra and switching algebra interchangeably. Okay, so actually in many sense, Claude Shannon is as great as the likes of Albert Einstein and Alan Turing. Actually, many people think he's on par. He's right there. Okay, he actually proposed this idea, right? So this idea, switching algebra, is the idea he proposed as part of his master's thesis at the age of 21. Okay, and later on, he also invented information theory, okay, which is the foundation of the modern communication systems. Okay, so that's why you guys should remember this name. And of course, for Boole, right? So make sure that later on when you guys spell Boolean algebra, right, this is a minor thing, but in our class, we should not try to make this always capitalize B, because this is named after Boole. Okay, so just a little bit of history over here. You may see some of this name again later on. Let me ask you a question first, right? Maybe, right? Since we are talking about algebra, right? All of you are exposed to algebra before, right? So what exactly is algebra, right? For example, for the algebra that you guys are familiar with, right? For example, you guys know there's 3 plus 5, right? It's the same as 5 plus 3, right? It's just so natural, right? But is this one algebra? Is this how do you define algebra? What exactly is algebra, right? So if you look at just this equation, right? You feel like this seems right, but this is not the whole thing, right? If this is the whole thing, then how do we also describe, right? Missing a lot of things, right? Like this two are also the same, right? Right, what's missing? What exactly is algebra? Very good, right? Emily saying, right, algebra has variables, right? Yes, David, you're saying the same, right? They use symbols. Okay, so we are actually missing the more abstract terms, right? More abstract symbols over here. So right now we are just using concrete numbers. So really the algebra, right? If you look at algebra as the study of how we manipulate the symbols, right? And same thing here. So for Boolean algebra, we don't just want to look at 0 1s, right? We actually want to first introduce what exactly are the symbols and how do we manipulate them. So that's where we need to introduce a few terms, right? Okay, one of you, Emily, already mentioned that we need variables, Okay, so that's where we define them. Okay, so we need to define the Boolean variables. Of course, they can be either 0 or 1, right, or true or false. We also know the operators, right, that can be applied to these variables, right? These are three important gates, right, and or not. So these are trivial, right? These are basic ingredients. And then we also need to define a few more terms. One important term is called literal. Okay. Right, so this one, we may have two forms of literal. Let's say we have a variable x. Okay, so in its original form, we call it a positive literal. Okay. Or we may negate it or invert it. Okay, we have x prime. With x prime, we have something called a negative literal. Okay, so basically for any variable, okay, we may have two forms, right? Either positive literal or negative literal. Okay, basically its original form or its complement. Okay, so that's a literal. And once we have the definition of literal, we get to define something called product. This is really related to the AND. Okay, so if you AND multiple literals and more than one, okay, together, we have something called a product term. Okay, this one is a product term, right? So this is where we have two literal, right, product term. And we may also have sum term. We're going to use product sum a lot, right? Because like I said, right, so you often just say like times or plus, right? So that's why you're using product sum. And this is a sum term with three literals. Okay, z is in this is negated, right? It's a negative literal, and x and y, they are the positive literals. Okay. All right, so these are some of the basic definitions, right? Just make sure that you are comfortable with these ones, right? We will see product and sum a lot in this lecture. Okay, we also need to define how we actually order things, right? So that's where we define the precedence. Okay, for example, what exactly does this mean, right? So do we calculate, this term first, right? Do we calculate n first, or do we calculate the or plus first, right? So this is where we have to define some order. Here's the precedence. Okay. This is pretty much similar to if you have happened to know some programming languages, right? This is very much similar to the same ordering rule that we are using. Basically, we always do the not, right? We do the prime first, then and has a higher priority than or. Okay. Okay, so given this expression, so this is what we are doing, right? We do not, and then we do the product, and then we calculate the sum. So later on, we may not use this many parentheses. Okay, just make sure that you remember the order. Okay. Some more definitions. We just look at what is a product, right? And what is a sum. And there's also something called normal term. So normal term means that in this term, either in the product or sum, every single variable appears and appear exactly once. Let me just try to be more concrete. Right? For example, for a 3-input Boolean function, x, y, z. So this one, this example, this is the normal product. Okay, x, y, z all appear, and they appear exactly once. And this one, for example, x, y times y, this is not a normal product. Of course, we can further simplify it, right? But this is not really a normal term. So when we have a normal product, we have something called min term, right? So this is a very important concept. Make sure that you remember, right? So when we have product term, and we have a normal product, we have something called min term. And similarly, we can define the same thing, right? A very similar thing for a sum term. Okay, if you have a normal sum, again, when all the variables appear once and exactly once, and if it is a sum term, then we have something called a max term. Okay, max term. Min max, right? Min means product, max means sum. All right. Okay, so these are the definitions, right? These are kind of dry right now, but we'll see how we actually use them pretty soon. Okay, so we just defined min terms, right? And max terms. you can probably guess already, right? Given a 3 input function, there are just so many minterms and so many maxterms that we can define, right? So let's say, we have a 3 input function again, right? X, Y, Z, right? Yeah, I'll answer a question later. Okay, let's look at this table first, right? We have a 3 input function, right? X, Y, Z. We have 8 input combinations, right? X, Y, Z. Right? So these are the input combinations, right? This column. For each input combination, or each input row in the truth table, right? So for each row or each combination, we have a corresponding minterm and max term. Okay. First, hopefully this makes sense, right? So we have 8 minterms and 8 max terms, right? Because in a normal term, right, each variable can only appear once, and it must appear once, exactly once, right? And they can appear in the form of either a positive literal or a negative literal, right? So that's why we also have 8. Okay, and so here's the way that we define the minterm, how we map the input combination. So this is really a mapping, right? So how we map each input combination into a minterm and also max term. For minterm, it's actually more intuitive, right? Okay, so if the corresponding input is a 0, we have a negative literal. Okay, see here, right? X, right? The corresponding input for X over here is 0. Okay, so we use X prime or X naught. Same thing for Y, right? Z, we use Y naught, Z naught. Okay, and etc. Right? So if we have 1, right? Let's look at this guy. Right, so this is a corresponding minterm. X is a positive literal, Y positive, Z positive. Right? So for minterm, if you have 1, you have positive literal. Okay, if you have 0, you have a negative literal, and you add them together. All right, so here's a quick question. So before I talk about max term, of course, these are just these are just a Boolean expression, right? We are using variables. So if you look at a given input, let's just say 0, 0. Okay, given the input, let's say the input are all zeros. So how many minterms are evaluated to 1? We have 8 minterms, right? We have 8 possible minterms. If I say that X is 0, 0, Y 0, and Z is 0, and look at all these minterms, how many of them will be 1? Okay, I'll give you guys a minute, right? So the answer already rolling in, right? Should be just 1, right? Exactly 1 minterms will become 1. The other minterms will be zeros. Does it make sense? Okay. Again, just plug it in, right? So we can easily plug in 0, 0 to the first minterm. So over here we call this small m0, right? You plug in all zeros, of course, this term, right? This term will be 1, right? We have, because all x prime, y prime, z prime will be 1, right? But if you look at other, like for example, this guy, right? So we plug in 3 zeros. Yeah, we try to plug in 3 zeros. This term is going to evaluate to 0, right? Because z is 0. Z is in the positive term, positive literal form. Okay, right? Hopefully this makes sense. Let me erase this. Okay, so this is a minterm, right? And also we come up with a shorthand, right, for these minterms. So we call the first one as M0, so, and the second one as M1, right? This is basically just directly corresponding to the corresponding input combination, right? If you look at this guy, M3, because if you translate this input combination into a decimal number, this is a 3, right? That's how we index the minterms. Any questions about minterm?
Yeah, quick question, Professor. Just to clarify, so the minterms are indexed by the specific series of variables x, y, and z that would make the minterm equal to 1, right? Is that how the indexing works?
Exactly, right. Right, very good question, Jacob, right? right? Basically, these minterms are indexed by a certain input combination that will make it 1. Just to repeat what you just said. Okay. Right. And also, yes, Andrew is asking whether there will be an item pool, right? So yes, so we'll actually do a quiz. So using item pool. And the quiz will be about minterms and maxterms. Right. So make sure you guys ask questions. Okay, all right, so this minterm, right? Then let's look at maxterm, right? Maxterm is slightly more confusing, right? But maxterm is basically just the opposite of minterm, right? You can just, in some cases, right, so if you're not really comfortable with the maxterm, you can write down minterm first and then sort of invert it in the way that you replace the end with or. Okay, see here. Okay, so everything, so this is maxterm is a sum term, right? It's a sum. Everything's an or. Use or instead of and. And if you have a 0 here, okay, then you use a positive literal for the maxterm. Right, that's it. So this is how we define maxterm. It's really the opposite to minterm. And we use big M, right, as a shorthand. And we are using the same index, okay, to name them. Right, same question again. Okay. So let's say, given a specific input combination, again, 0, 0, 0. If you look at all the 8 possible maxterms, how many of them will evaluate to 0? Also 1, right? Exactly 1. And the rest will become 1. Hope you get that idea, right? So for minterms, right? So given the input combination, a specific input combination, out of these 8 minterms, 1 and only 1 of them will become 1. Okay. But for maxterms, okay, same question, but there it's opposite, right? And exactly 1 of them will be 0. All right, so we'll see, why this makes sense, right? We'll see it pretty soon. Okay, all right, so these are definitions, right? So we're going to do some exercise. So just to make things, a little bit more concrete. But let me introduce a few more terms, right? I also need to introduce something called canonical form. Right? So this is where, if you have 2 functions which are functionally equivalent, we actually want to, in many cases, want them to have the same representation. So that's where we want to canonicalize certain things, right? So that's where we have something called canonical form. So actually, true stable is a canonical representation for a Boolean function. Okay. So we'll soon find out later on in this lecture. So these 2 things are actually the same. Right? There's something called De Morgan. So these 2 are the same. These are the same Boolean functions, although we can actually write them in many different ways. Right? So these are just 2 different ways to write them. But if you convert these 2 functions into a true stable, you get something canonical. Basically, both of these, both of these expressions, right? These 2 will have the same true stable. That's why I call them canonicalized or canonical. And of course, with true stable, we use 2 to the n, right? Given any input function, we have these many rows, and these may not be, scalable, right? In many cases, right? If you have a large function, if you have to use true stable, let's say 16 input, right? It's going to be a lot of rows. So that's where we also look at whether there's other. Okay, we also want to look at whether there are other canonical representation that we can use other than the true stable, which are hopefully more compressed, okay, more compact. So this is where we're going to introduce something called canonical sum, which is really just based on the, the minterm, and canonical product, which is based on the maxterm. It's also called SOP or POS, and we can explain this. And there are even other more compact forms exist, like based on graphs and other things. This is actually really based outside of the this lecture, also the course. We're not going to touch on those. In this course, we're only going to look at true stable, right? This canonical sum and canonical product as the canonical forms. Any questions about the concept of this canonical form? Right? Again, if you have 2 different functions, they are simply the same. Yes.
What do you mean when you said that 2 to the n rows required for an input function?
Right. So you're asking about this one, right?
Yeah.
Okay. Right. So again, if you look at AND gate, right, the 2-input AND gate, right, 2 input. We have in the truth table we have 4 rows, right? Is that right? Think about the truth table AND gate, right? 4 is 2 to the 2, right? Right. So for 3-input function, we just look at 1, right? There we have 8 rows, right? 2 to 3. Right. In general, for any input function, we actually need exponential number of input rows.
Okay. Yeah, but does are the 4 rows just because you chose a function that is simple and only has and? Like if it were a more complex function with or also, it would have a different number of rows?
Oh, so no. Again, so this is actually independent from the kind of function that we are dealing with, right? So whether we are looking at AND gate, OR gate, or any arbitrary Boolean function, okay? It's really about how many input combinations do you have, right?
Okay.
So for n input function, Boolean function, we have 2 to the n number of input combinations.
Okay.
Make sense?
Yeah.
Right. So
got it. Thank you.
for 2 input, right, we have 4 input combinations. That's where we have 4 input rows in the truth table.
Got it. Thank you.
Good question. All right, so let's first look at canonical sum. It's also called canonical sum of products, or canonical SOP. It's really a sum of minterms. So this is one way that we can use to represent the Boolean function in a canonical way. So the way we do it is we look at the onset, okay? So the one in red. Okay? The onset. So the onset means the input combinations that make F a 1. If you look at this table, right, the onset is already marked as red. These are obvious, right? So which ones are on? And the zeros, later on we'll see that, those are offset, okay? If you look at this onset, right? So once we get onset, then all we need to do is to write down the corresponding minterms, okay? And then just sum them up. That's it, like this. Right? You know, we have 4, right? 4 input rows in the onset. And we just write down the corresponding minterms. And we sum them up, we get our function. Hopefully the intuition is clear, right? Okay, because you know we get a 1, right? If we hit one of these input rows, right? So that's why we order them together. And we already discussed, right? Given any input combination, right? Only one and only one of the minterms will be a 1. Right? So as long as we hit one of them, we're done, right? We cannot hit any of them, right? So you know, if this one, so like if all 4 of these eval to 0, so that means the input combination is in the offset, right? So that's where F is a 0. Any questions about this truth table? Philip is asking, is this the same table from before? May not be. Yeah, I did not check actually. So this might be a different example. Okay, great. So this is just an arbitrary function. Any questions about onset? And
yeah, I have another quick question about the onset. So basically, is the whole function basically saying, given any, if you hit any of these combinations in the onset, then it will be 1. So is it basically just like a set of all the
that's right
minterms? Or,
that's right. Yeah.
Yeah.
That's right.
Okay.
Yeah, you get the right intuition, Jacob. Right. So yeah, like I just mentioned, right? So if we hit any one of this, right? Any one of this, so then one of these terms will be a 1, right? Since these are all together, then the functions are for 1, right? Otherwise, you know, if you are not hitting any of these red columns, that means we are in the offset, right? So then all this will be 0, right? So then of course function is 0. Okay. Right. Yeah, almost Gaussian, right? So it's the only way to describe the function given a true stable. This is one way to describe the function that we may or may not use the true stable. Okay, but in this class, in most cases, we'll give you the true stable first, okay, and ask you to describe, right, what is the canonical sum. All right, so this is the canonical sum, and let's look at the. Oops, somehow my pointer is small. Okay. Oh, there's one more question. Okay, let me just clarify. So if there's one of the mean terms is 0, yeah. So Rushi is asking if one of the mean terms 0, but the rest is 1. Would that be still on the offset? So first of all, only one of the mean terms can be a 1, right? We already discussed that. Given any inputs, so only one of the mean term will be 1 at most, right? Right. So that's something to remember. All right, so let's also look at this canonical product. Okay, so this is about max term. So this is where we actually multiply the max terms. So over here, we look at offsets. Right? So what exactly is offset here, right? So this is where, we make F0. Okay. And we just look at the everything, right? All the input combination in this offset, and then we just write down the max terms, and then we multiply them together. That's how we define a canonical product. Okay, so what's the intuition here? Right. So the intuition here is that, if we actually hit, right, any one of the input rows on the offset, okay, so one of this will be a 0, right? If one of this is a 0, then the entire thing becomes 0, right? The only way that we get a 1 is when, we avoid the offset, right? If you avoid offset, I need to clear this up. If you avoid offset, right? So, if we happen to be here, 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 or here, so that all of these terms will be 1. Okay, and we end them together. That's how we get a 1. All right. So this is the definition of canonical product, right? Actually, this canonical sum and canonical product, they are actually, to some extent, very much the complement, right? The moment that you calculate the canonical sum, then you can directly look at the complement, the opposite part, right? And you get the canonical product. All right. What's the question? The product really means the end. Yes. So multiplication and end, in this case, they are the same. Okay, so but why, right? I've been introducing all these sort of convoluted terms, right? So why are we doing this, right? So why are we introducing both, right? Min terms and max terms. So let's just do some exercise very quickly. Let's look at the things that we love, right? We're already familiar with, right? NOT gate. What is the canonical sum over here? What's in the onset? This guy? No, right? This is the onset, right? Small m0, right? How do we spell it out? This is just, right? A is 0, so for min term, we invert it, right? A prime. For canonical product, this is the offset, right? This guy, offset. So A is 1 for max term. Yeah, remember for max term, when A is 1, we also use a negative literal. Right. Make sense, right? So this is trivial, right? How about this guy? C sum. Canonical sum is min terms, right? How many do we have in the onset? Just 1, right? 1 row. Okay, A and B. Right. Let's move on, right? How about OR gate? if we just use canonical sum, what is the expression? We have three things on the onset, right? I think sorry. How ugly this thing is, right? This is not the OR gate that we love, right? Okay. So how do we get the OR gate? How do we get the OR gate that we want? We look at the canonical product, right? So if you look at the canonical product, so we just need to focus on this row, right? Which is what? A plus B. Is it clear now? Hopefully, guys. Right. So really, the reason that we have both, right? Because for some functions, it may have a lot of ones, right, in output columns. Okay, so that's where we we look at the offset, right? For some other function, we have a lot of zeros. That's where if you want to come up with a canonical form, we look at the onset. Right. Okay, I think there's a question, Andrea.
Yeah, so just to understand, are the canonical sums and canonical product like ways to represent functions so that it's easier to see the onsets and offsets?
Yes, they are the same, okay. Right? They are functionally the same. Right.
Okay, so the reason why you use the C sum in the second example is because it's much simpler. It's just okay, right. Got it. Thank you.
It's much more compact. Right? Hopefully you guys agree.